Welcome to The Explainer. Today, we're diving into a topic that is absolutely essential for anyone who messes with electronics, whether you're a hobbyist or a total pro. We're talking about resistor power rating. Get this right, and your project works. Get it wrong, and you get a puff of smoke. But let's start with a really basic question. You've definitely felt this. You're holding your phone, it's been working hard, and it's warm, right? Or maybe your laptop gets really hot. Ever stop and wonder why? Well, the answer isn't always about some super complex processor going crazy. A lot of the time, it all starts with one of the simplest, tiniest components in a circuit and a basic law of physics that you just can't escape. So here's how we're going to break it all down. First, we'll look at why electricity has this hot problem. Then we'll talk about the solution, something called a power rating. After that, we're going to get our hands dirty with a little math. Don't worry, it's easy. Then we'll explore the different kinds of resistors out there. And finally, we'll wrap up with the one rule you absolutely have to remember to keep your circuit safe.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, section 1, electricity's hot problem. And we call it a problem, but really it's just physics doing its thing. It's inevitable. So here's the deal. A resistor's main job is to, resist the flow of electricity. But all that energy it's holding back has to go somewhere, right? It doesn't just vanish. It gets converted directly into heat. And the more current you try to shove through it, the hotter that little guy is going to get. Simple as that. So if making heat is just part of the job, how on earth do we manage it? Well, that brings us right to the solution. And it's called the power rating. This is the whole key to keeping that heat under control. So what is it exactly? Think of it like this. A resistor's power rating tells you the maximum amount of heat it can safely get rid of, or dissipate, forever, without burning itself out or getting damaged. You'll also hear people call it the wattage rating. It's basically the resistor's heat endurance level. And the main idea here is surprisingly simple. A resistor's power rating is pretty much all about its physical size. A tiny little resistor has a small surface area, so it just can't get rid of heat very fast. But a bigger resistor, it has way more surface area, so it can radiate that heat out into the air much more effectively and safely. It really is that straightforward. Okay, time to get practical. How do we actually figure out how much power, how much heat a resistor is going to have to deal with in our circuit? Well, this section is your toolkit. All right, tool number 1, the big one. Power equals voltage times current, or P equals V times I. This is your best friend when you know the voltage across the resistor and the current flowing through it. Super simple, super direct. But what if you don't know the voltage? No problem. If you know the current and the resistance in ohms, you've got this formula. Power equals the current squared times resistance. This one is super useful, especially in series circuits, where the current is the same everywhere. And for our third tool, let's say you know the voltage and you know the resistance, but you don't know the current. Then you use this. Power equals voltage squared divided by resistance. This is perfect for parallel circuits where the voltage is always the same. So, 3 tools for 3 common situations. Let's actually use one of these tools right now. Imagine we have a circuit with 12 volts running across a resistor, and we measure 50 milliamps of current flowing through it. That's 0.05 amps. Since we know voltage and current, we grab our first formula, P equals V times I. We just plug in the numbers, 12 volts times 0.05 amps, and we get 0.6 watts. That's it. That's how much power that resistor is going to be turning into heat. Okay, so we can do the math, but what does that number actually mean? What do we do with it? Let's take a look at the different kinds of resistors you'll actually find in the real world. This little table tells the whole story. It's all about trade-offs. On one side, you have your standard metal film resistors. They're super precise, really stable, but they just can't handle much heat. Carbon resistors can take a little more power, but they're not nearly as precise. And then you have the heavyweights, the wire-wound resistors. These things are built to handle some serious power. Yeah, let's just focus on these powerhouses for a second. Wire-wound resistors are made for heat. They are literally a special kind of wire wrapped around a ceramic tube, a design that's meant to get hot and stay stable. We are talking hundreds of watts. You find these in really heavy-duty stuff like motor controls, braking systems on giant machines, and get this, in your toaster. Their entire job in a toaster is to get hot and make toast. And that brings us to our last and, honestly, our most critical section, making the right choice. Because knowing all the theory is great, but applying it safely, that's what really counts. So what happens if you get this wrong? What happens if you use a resistor that can't handle the heat? It doesn't just quietly fail. It overheats. It burns out, often with that classic puff of magic smoke, and it can very easily destroy other, much more expensive parts of your circuit along with it. So here it is. If you remember one thing, just one thing from this entire explainer, make it this. Whatever power you calculate that your resistor needs to handle, you always choose a resistor with a power rating that is at least double that value. So for our example earlier, where we calculated 0 0.6 watts, you don't grab a 0.75 watt resistor. No, you jump up to a 1 watt or even a 2 watt resistor just to be safe. That safety margin is absolutely non-negotiable. And hey, that's not just my opinion. The source material is crystal clear about this. This quote says it all. Choosing the wrong resistor doesn't just mean that one little part fails, it means your entire circuit is at risk. So the next time your phone feels warm in your hand, think about this. Deep inside that device, there are thousands of tiny components, and every single one was chosen with a specific power rating in mind, all part of this incredible, complex dance of thermal engineering. Makes you wonder, doesn't it? What other hidden engineering is going on in there, all working perfectly just to keep that device from melting?
Thanks for watching.